Hello! In this video, we'll talk about the other machine language formats for RISC-V. So, second format is I-type. This stands for immediate type. And I-type instructions also have three operands. They have a first source register, they have a destination register, but instead of having a second source, they have a 12-bit immediate. Like R-type, they have an opcode, and like R-type, they have a 3-bit function code, but they don't have room for another 7-bit function code. So the I-type instructions, like R-type, have the op down at the bottom. They have RD and RS as two 5-bit fields like before. They also have the funct3 field of I-type, but instead of having an RS2 and a funct7, they have a 12-bit immediate in the upper bits. And that's for instructions like add I, that could do add I, say R x5 gets x3 plus 42. The op and funct would represent add I, rs1 would be x3, rd would be x5, and the immediate would be 42. Here's some examples of that with an add I. S0 is x8, S1 is x9, and constant 12. So the opcode for add I, look in Appendix B, is 19, and its funct3 is 0. The destination register is S0, the first source is S1, and the immediate is 12. And just the same way as with R-type, we pack these into bits, and we can express the 32-bit instruction in hexadecimal. Here's an add I with a negative immediate, and so now the immediate is minus 14, which is a 2's complement number, is this. Another example of an I-type instruction would be a load. For instance, load word has an opcode of 3, a funct3 field of 2. The destination register is T2, which is register 7. The base address is RS1, it's S3, which is number 19. And the offset here is -6. There's also, we've talked about load byte. We haven't mentioned load half word yet, but load half word is like load word or byte, but it loads 16 bits. So load half word has the same op as load word, but the funct field is different. And load byte also has the same op, and again, a different funct field. S and B type instructions are for stores and branches, and they differ only in the encoding of the immediate. So, like the other instructions we've seen, they have an op field, the bottom 7 bits, and an RS1, 5 bits of source. These take a second source in the same place as the R-type instructions had them. They also have the funct3, like all the other instructions we've seen. They take a 12-bit immediate. For an S-type, the immediate has the bottom 5 bits here and the upper 7 bits here. And the reason that we couldn't put them all in a row like an I-type is we needed this second source. B-type is for branches, and the least significant bit of a branch offset is always 0, because branches are always by an even amount. So there's no need to store immediate 0, because that's always 0. So instead we can store a 13-bit branch offset, bits 12 through 1. And they're in a bit of a funny encoding like this. And we'll come back and look at that further later on. So here's S-type again, just like we talked about. And some examples of store instructions using the S-type encoding. All the stores have an op of 35 and a funct. A funct is 2 for store word, 1 for store half word, and 0 for store byte. they have 2 source registers and an offset. So an offset of -6 in hexadecimal, or -6 is a 12-bit number, is 1111111010, makes -6. So we pack the bottom 5 bits in here and the upper 7 bits up here. Store half word and store byte are similar. B-type, again, are similar format, just the way the immediate is stored. So let's say we wanted to do BEQ. If S0 is equal to S5, we want to branch to label 1. So this instruction is at address, say, 70. Label 1 is at address 80. It's 4 instructions later. So we need to add 16. These are in hexadecimal, so 70 to 80 is hex 10 or decimal 16 bytes further in the program. So we need an immediate offset of 16. And 16 is a bunch of zeros, a 1 in the 16s column, no 8s, no 4s, no 2s, no 1s. But remember that branches are always by an even amount, so there's no need to store the least significant bit, so we won't even encode it. So we need to store now 12 bits, but they're bits 12 through 1 instead of 11 through 0. And we need to find where they go. So bits 1, 2, 3, and 4 are 1, 0, 0, 0. They're going right here. Bits 5 through 10 are all zeros, and they're the blue ones going here. Bit 11 is this 0, and it goes here, and bit 12 is that 0, and it goes here. So you see the process of doing this by hand is kind of tedious to encode the branch. A computer will do it for you automatically. That program is called an assembler to do the encoding. But the key for a branch is to figure out what the offset needs to be. In this case, it's 16. It's what we need to add to 70 to get up to 80. And then we have to stick those offset bits in the appropriate parts of the immediate field. U and J-type instructions are also similar. They have an op, a destination register, and a 20-bit immediate. U-type instructions are used for load up or immediate. J-type are for jumps. So U-type takes a 20-bit immediate that is just in the upper 20 bits, and it's the value that we want to load. J-type, jumps are by an even amount, so there's no need to store the least significant bit, and they're munged in a kind of funny order here. And again, we'll see in a little bit why we do that funny order. So U-type for load up or immediate. Let's say we wanted to do an LUI of S5 gets 8C, D, E, F. The opcode for load up or immediate is 55. Register S5 is number 21. And then the 8C, D, E, F goes in the upper bits. And our instruction is 8C, D, E, F, A, B, 7. For J-type, these are used for jump and link. So got to be careful with this funny ordering of the immediate. Let's suppose we were at 540C, and we want to do a jump and link RA to funct1. And funct1 is up here at address 1ABC04. So 1ABC04 minus 540C, well, 4 minus C we can't do, but 14 minus C is 8. We'd had to borrow 1, get an F here, and a B here. f minus 0 is f, b minus 4 is 7, b minus 5 is 6, a minus 0 is a, and 1 minus 0 is 1. So funct1 is an offset of 1a67f8 bytes past the jump and link. Now, that offset, since it's even, again, we aren't going to store the least significant bit of it. That's implicitly 0. And writing this number, 8 is the 1, 0, 0, 0. F is all 1s. The 7, this is 7. 6, A, 1. So we need to represent this as all those bits and pack them into the right place. So we put bit 20 up here, then we put bits 10 through 1. 10 through 1 are this 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, which are these 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. Next, we have bit 11, the blue one, goes here, and then bits 19 through 12, 19 through 12 are these. 1, 0, 1, 0, 0, 1, 1, 0. 1, 0, 1, 0, 0, 1, 1, 0. So that's the immediate packed in this funny way, and our machine code is this. So in summary, here are the instruction formats in RISC-V. All the instructions have op in the same place. So that's how you figure out what type of instruction you're looking at. You look at the bottom 7 bits, and based on the op, you decide what type of instruction you're doing. All the instructions that take a funct3 also have that in this middle position. You'll notice all the instructions that need an RD have it here. All the ones that need an RS have it here. RS1, RS2 have it here. And then R-type instructions have 7 more bits available for funct. The other types of instructions have an immediate, and it's packed into various places. So this is a good example of design principle 4, that good design requires good compromises. So we've got multiple instruction formats to allow flexibility. For instance, add and subtract need 2 sources and a destination, while something like load word, store word, or add-I only need 2 registers and a constant. If we'd had 3 source registers and just disregarded one of them, say an add-I, that would have taken up 5 bits of the instruction, leaving only 7 and 12 instead of 12 bits for add immediate, and it wouldn't have allowed us to have as many immediates. On the other hand, the number of instruction formats is kept small to adhere to principles 1 and 3, that simplicity favors regularity and smaller is faster. So by having just a small number of instruction formats, we get the flexibility we need while still allowing a fast and simple decoder.